actually you couldn't write anything useful with Haskell because all real-world programs have side effects, obviously, and they do those side effects via input-output of various kinds, such as text-based input-output, or file system, or sending packets over network, or generating random numbers, which is also a side effect that ruins your purity because the function no longer returns the same value every time it's called. So the side effects usually come at a cost, right? Because you have to set up and tear down the environment you call your functioning. So for instance, for testing, you would have to clean up the environment, remove all side effects that the function has created, and test it again, right? And to simulate all the side effects, you would create elaborate mocks, right? Like huge data structures to validate the output of the function against. And that wasn't very, very nice and easy. So how could real-world useful programs be written in Haskell? To solve that, they came up with something called the I/O monad. And I'll be getting to the concept of monad in a few slides. So basically, the authors of the language said, wouldn't it be nice to have some kind of type that would allow us to have side effects, but would also be composable? So basically, the same we do with pure functions, but with side effects ingrained. And they call this type I/O for input-output. And you might be used to data types such as int or string or an array of floats or whatever, but I/O was supposed to be a computation type. So your entire program would have this type I/O of something. So you receive a value of type C, and with some side effects. A file is written somewhere, a network packet is sent, something is written into a database. A missile is launched somewhere, God forbid. So to preserve purity of the language, they did the following, that your program would only generate a computation that would cause side effects later. And the runtime, the Haskell runtime, when you actually run your program, would evaluate this side effect in computation. And then side effects will take place. Let's model this with JavaScript, because we all speak JavaScript here, right? For instance, how can we defer computations? How can we make them happen later and not immediately? We can do it by simulating lazy evaluation. And we can do it just by wrapping some values into functions that are not called yet. So I can come up with a simple lazy constructor, and then I can wrap values with it. So I can get a lazy number 5 here by just creating a function that returns number 5 when called. And then the problem is that I'm used to have all the comfort working with numbers just like that, by, for instance, applying functions to them, adding numbers or negating numbers, but I can no longer do that with lazy numbers. So in order to do that, I come up with a different function, I call it map, which would kind of work with those lazy functions that return values and apply functions inside those functions. And to do that, you can see it's really simple. It's just functional composition. We just merge functions together. So let's say we have a function that returns some value of type A, and then we want to negate it or apply any kind of function that may return a different type B. So we just compose those functions together, and we have another function that returns the value of type B. And then it achieves that without evaluating the function, so it's still lazy, right? So to negate our lazy value, we would just apply map to our lazy 5. And likewise, we can have lazy side effects. So we can wrap functions that are regularly associated with side effects, such as having console or text-based output. We can wrap console log, or we can wrap prompt. This one that brings up a pop-up and asks you to put a value here in the browser. It's still supported. It's terrible to use it, but it's still there. So even random, right? We can have a function that is not evaluated yet, right? But that when evaluated will call math.random and will produce a random value. So all side effects we can kind of wrap into functions that are not called just yet. So why don't we call this a type, right? So when we wrap something into a function, some type A, right? Why don't we just call it IOA? So our prompt would have thus the type IOString, and log would be a function from string to IOUnit, and unit is just a type that has a single value. Or it's not a very interesting type, of course, but you have to have some type in functional programming. You can just return undefined. So it's not nice. So as you can see, prompt, when evaluated, will eventually give us a string. And log is a function that's like, give me a string, and I will give you a computation that when evaluated will give you a unit. And what you do with it is whatever. So what we want to do is we want to bind those two functions together. We want to compose them, because that was our original goal here, right? We want to make entire programs out of those functions. So I need to write some function, let's say I call it bind, that kind of first prompts the user to input something, and then logs it. But the whole thing is not evaluated just yet. I just want to create this program, this computation that I will later run. And to achieve that, I can simply do the following. Let's say I have a function that returns a value of type A, and then I have a function that transforms it and returns another lazy computation, and I want a computation of type B as a result. So given a lazy value of type A and some function, I just first evaluate the L A by calling it. So I unwrap it, and then I apply F to it, and I get the new lazy value that I will later evaluate, right? But the catch here is that I'm doing that inside of a function, so I still don't evaluate anything until this wrapping function is called. And once those functions are called, they will have those side effects that they're planned to have. They will print something on the console, they will produce this ugly pop-up in the browser and ask the user to input something. But that will happen when everything is evaluated. This entire computation merged together. And the cool thing here is the computation shape, the type signature remains unchanged, so I can link new computations to it over and over again. And the type remains the simple function that returns something once called. So to bind prompt and log together, I just call my bind function to compose those two functions. But when I really want the side effects to take place, I will have to evaluate once again. And in Haskell, they decided to be huge trolls about it, and they came up with syntax sugar for bind, for this bind function, to make it look like imperative programming and to deceive the imperative programmers. So they would say Haskell is an imperative language. Like, what's the deal with it? So here you can see that we write it in a similar manner to an imperative program. We read something from prompt, we call it name, and then later we log it. While in the background, that translates to a series of bind functions. And that's a very sneaky thing to do, but it's also very powerful. I'll show you a bit later. So to recap, with I/O, with this approach, create a lazy computation, apply functions, and then evaluate it once the program is run, we get the following benefits. First, all the functions we have are still pure. Every function is still pure. We don't have any side effects when we compute the program. And then using the map function and the bind function, we can reuse code. We can still apply functions such as negate or add to values inside I/O. And another great thing is that once you start getting I/O, for instance, you started using the console log function that returns you an I/O value, you can't get rid of it. You can only work with it. You can only work with the values together. You can unwrap it. You can go from I/O of A to A. And that's great, because once you start having side effects, you can't really stop having side effects because they're already there. The world is changed. It's too late. And another great thing is that this way, effectful code and pure code is very cleanly separated. So you can modularize any way you want. You can write many pure functions, keep them in modules, test them very easily, and only then apply their compositions to values inside I/O. But I/O is obviously not the only type that works like that. There are many types, right, that have, well, let's say complications, but they're not very easy to deal with. So, for instance, we have a value of type E, but then the value can just not be there sometimes, or it can be undefined or null. You know such functions that are very sneaky and return null sometimes when you least expect it. And then you can have collections of values instead of a single value. You can have a promise of a value that is, will arrive sometime in the future. And you can have a stream of values such as reactive streams like RxJS or Bacon. And yeah, our I/O is one of those types of complications. It describes a computation that is yet to happen as well. So something similar to a promise, actually. So how do we work with those types? And the cool idea in functional programming is that you derive all types using, well, math. If we look at our simple types such as int or bool, we can realize that they're just sets of values. And sets are mathematical objects that we can work on, right? So int is a set of numbers, of integer numbers, negative, positive, 0. And then bool is a set of two values, true and false. And we can define functions between those two sets by mapping single components, single elements of those sets. For instance, the function is odd here goes from int to bool, right? It checks if a number is odd and returns true or false. Now, we can construct a type with a complication. For instance, a nullable int, that is an int or a null. We can just extend the set of numbers, but with one more value, which is null, right? Or undefined, if you prefer undefined, but why? And boom, you have nullable int, nullable bool. But what about our function f? It works on int and bool, but it doesn't work on nullable int and nullable bool. So we can fix that by just checking for null, right? So if f gets a null, it has no other choice but to return a null. And otherwise, it can apply the function that is defined for int and bool, for simple types, right? So that's kind of my take on this function in JavaScript for nullable types. I expanded it on purpose a bit. And this function is called map, traditionally. So you see it, the function f, it returns a new function that will work on nullable types, including this null check. So what are we doing there? We get a new type. This nullable type, for instance, in Haskell it's called maybe, in Rust and Scala I think it's called option. There are many different names to the same thing. So we get a new type based on the old type by just extending its set of values, right? And then the functions defined for the basic types that we use for derivation, we also take them together. We also take them into the new type by just applying the map function to it. And we can define map function for every type like that. We can define map for maybe. You saw we defined map for our lazy type, for our I/O type, and so on and so forth. And you can see that maybe is actually a function on types. So the power here is that you can see types as values and write functions that work on types as values. So a function on types gets a type as an argument and then returns a new type. So you call this construct a functor. So for instance, maybe is a functor. That is, it has to have a transformation of a type into a different type, such as from bool to maybe bool, to a nullable type. And it also has to move all the functions defined for simpler types into the derived type. So a functor is defined by the way it extends the simple type and the way it maps the transformation on simple types into the new derived type. And that's the typical diagram they draw when they want to talk about functors. I even saw it on the pavement, draw with chalk one time. As you can see, if you follow either green path or the orange path, you arrive to the same corner to the value f of b, right? So it doesn't matter if you first apply a simple function and then you go into the functor, or you first go into the functor and then you apply the mapped function f. So if your construct follows that, it's a functor. There are also a few laws, but I really tried to cut back on math for this talk. And you all know the array functor and its map function and what it does and how it works. So array functor can give you an array type for every type you have. You have a bool, you can have an array of bools. And the map, if you have a function, let's say from int to bool, you can still take it into the array by just applying it to every element of the array. And it's actually called map, right, in JavaScript. The cool thing here is that you can compose functors. You can apply functor not once or twice. You can do it a lot of times, actually. So for instance, you can go to maybe a from a, and then later you can go to an array of maybe a. And the function f defined for simple types also goes together into all those complex functors by just applying map of the respective functor several times. And to change the way it's composed, for instance, to go from an array of optional values that may not exist to an optional value to an array that may not exist, right? So it can be either null or an array. You just have to rearrange the map function composition. So here we first call array, and then maybe, and then here we call maybe and then array, and the same goes for the map functions. So functors are composed completely symmetrically to the way we compose those map functions. And we still reuse this little f function we have in the very beginning. We don't have to write a new function, because those map functions are usually part of a library that comes with those functor types, like map function is a part of the array prototype object in JavaScript. So we just have to pass our simple function into the map function, and we get a new function that works in new types. So that's kind of the ideology of working with functors. So all these types can be functors, right? Optional values, list of values, promise of values, streams of values. We just have to define how they extend the basic type and how they map transformations to work with values of their types. For instance, if we add numbers, we can also add optional numbers that can be nulls by just lifting or just moving the add function into the maybe functor by using map, right? And the same goes to lists and promises and IO too, right? Like we can have two numbers obtaining, which will result in side effects, but we can still add them and get a sum. Evaluating this sum will yield side effects for both of those numbers. And the same for promises. We can add promise of a number to a promise of another number and get a promise of a sum. Yeah, and we can build very complex types as we like. For instance, we can have a promise of a list of optional values of type A. And it still works for every type A. So functors allow you to take your functions from A to B to functions from some f of A to f of B. But you often write functions that start with simple values and end up in the functor. The same way we wrote the IO functions that have side effects. So you start with a simple value and you end up with having side effects. Our other examples include lodash get, where you may or may not get the value from an object by key, right? So it returns a maybe of some type from a string, and then the fetch function that does a request. It doesn't return the value immediately. It returns the promise of the value. And consider a function that factorizes a number, that produces all the factors. It returns an array of numbers, or taking only a single number. So again, we want to compose those functions because we want all our functions to be pure, and we only have composition as a tool. We can't write statements as an imperative programming. So to compose those, if we align them like that, so if we have a function from A to functor B and B to functor C, and we want to compose them, they don't align because B is not the same as functor B, right? But it's always the same. It's almost there. If we take a slightly or different approach and we actually map our function from B to FC into the functor of F, right, by applying map to it, we'll arrive to a functor twice applied, f of C, right? Because we have to apply functor to both the argument and the result type, which is not very convenient because who needs a maybe int? It's not very useful to work with, and nor does anyone need a promise and a promise, and so on and so on. So it's natural to join those functors into the same, into a more flat level, to flatten the functor. And actually, the functors that are capable of being flattened are called monads. And that's all there is to it. There is, of course, a formal, strict mathematical definition, but it's not really interesting from the practical point of view. But if you're interested in that, we can talk about that during the break. So if we do this join function, right, that flattens the functor, we achieve what we want. In the first place, we wanted to compose A to f of B and B to f of C. As a result, we would get the function from A to f of C. Now we know how to go from A to f of C, right? First we apply f1, we get fb. Then we map f2 into f, and we get f of C. And then we flatten f of C with join, and get just f of C. So for every monad type, we have to define how this joining happens, right? So for instance, well, actually, I'll show you a few examples. And look at our bind function, right? It's the one we defined for IO. It starts with a functor value, and then it takes a function that returns, again, a functor value based on a simple type value. But then we don't see any double layer in the result type. We see only an f of b. And bind has to be defined this way so that it does the joining inside. And we also need our function, typically called pure, that allows us to go to our simple value into the value in a functor. In this diagram, it's this it's function from b to f of b. That has to be possible. Now, for an example, you can check this. An array is a monad because you can apply functions that return arrays to an array. So you have an array of arrays, and then you can flatten this array of arrays into an array with a single-dimensional array, right? Just one dimension. And you know how to do that, right? You can just apply concat or something. So pure function would be a function that creates our single value array out of a value of any type. Then the map function would be just map. You're all familiar with that. And then the bind would be just flat map, right? It applies a function, the function returns an array, and then we just flatten all those arrays. And still get an array, one-dimensional array. There are many more examples of monads, and I would really be happy to talk to you about that, but unfortunately it's a vast subject. So just to give a few examples of what you can do, what you can just flatten, and what types you can derive. You can work with continuations, for instance, that are callback-based values. You can link computations that rely on callbacks to go on together, right? So in JavaScript, that means that you can link together asynchronous computations. And then state modification can also be pure, or you can link state modifying computations together, and then as a result, you will get one computation that will modify the state in many different steps, and many, many more, of course. And they all work the same. That's the beauty of a monad. So once you understand this abstraction, you can really write a lot of code that repeats itself. You can really dry it, you know. You can just abstract this away and write simple functions and reuse them in different monads. So the scheme, the blueprint that the monads follow is that you always have a computation so far. The same we have in I/O. So we have a computation that will eventually produce a string or an int, right, when evaluated. We don't know what side effects are lined up in this computation, but when evaluated, it will produce a string. So we just kind of want to plug in a new function with another side effect into this already existing computation. And that's what bind allows us to do with I/O. And the same with maybe. We have a bunch of functions that may possibly fail and return null instead of the value we expect. So if that happens, we want to break out of the chain immediately and return null. So that's what the maybe monad does. We can link failing functions together and either get the value we expect from the last function, matching its type, or null. And it doesn't stop there, of course. And you can combine monads to form new monads with different flavors. So there are tools for that, types called monad transformers, that you apply to existing types, and you get new monads. So for instance, this type, remember the functions on types, right? So you can see it as a function on type. It works on any type A. It will create a computation, it defines a computation that can modify state of some type, state type, and then it can fail, and the error type would describe the error with which it fails. It can fail at every step of modification. And it has side effects, which is described by the I/O type. And then eventually it will also produce the value of type A somewhere. And for instance, promise is almost monadic in JavaScript. And there are a lot of things in JavaScript that are almost monadic. So with monad transformers, promise could be defined as something like that. You use continuation monad to define callback-based computations. And then the callbacks would accept some type result, right, once they're called. And then they can all still fail, right, with some network error or any error type, really. And they all have side effects of creating XHR requests and sending it using the browser capabilities, and so on. And finally, I would like to show you an article that I really wanted to copy it into my slides, but then I thought it wouldn't be right. So it's called Escaping Hell with Monads, and it's a really cheeky trolling of all JavaScripters. I felt immediately something in the lower back, some kind of nagging pain when I read this article. What I mean here is that the author says that in JavaScript you write all this verbose code, right, which you can rewrite with monads and do notation. Remember, do notation, that is just syntax sugar for all monads, which is just abstracts the bind function away, right? So instead of checking for nulls, there is a stage 1 proposal right now to ECMAScript to introduce the Elvis operator, this question mark and dot. But instead, you can just use do notation in maybe monad and bind those possibly failing functions together and write it in a clean way. And then when you iterate, right, when you have nested for loops in imperative programming, and instead some languages such as Python or CoffeeScript have list comprehensions, which is yet another syntax construct you don't have out of the box in other languages. You can use the list or the array monad, right, and still use do notation to link the computation that produce arrays together. And of course, callback hell, right, which was combated with our async and await in the recent edition of the ECMAScript spec to make it look nicer, for Christ's sake. Like, after all those years of writing next and callbacks and so on. And then you also use promises, right? So when one relies on the other. Instead, you can use continuation monad that links the callback-based computations and still use the do notation to make it look nice. And of course, there is state passing hell, which is just linking or mutating computations that produce some values. And in imperative languages, okay, we have it easy because we just write statements and they're executed one by one, right? In the exact same order we wrote them in. We can do that in Haskell too with do notation and state monad and achieve the same syntax, even though all those functions are still pure functions. Yeah. So that's really nice, that instead of adding new syntax constructs, there is a syntax construct already defined for that, and that is do notation. It works for all monads, so that you can define your own monad or build your own monad out of existing monads. And do notation will still work for that. So let me just conclude. In functional programming, it's typical to play around and create types out of existing types using functors, monads, monad transformers, and other exciting higher order type functions and constructs. And the cool thing here is that you can still write just simple functions and then reuse them with those complicated types, following simple laws and using some wrapping functions. And all of your code remains pure. And that's a very important quality because it makes your code easily refactorable and easily testable with tools such as generative testing or even formal proof systems, which basically work on predicate logic and can verify that your program is actually correct, that not only do all the types align in your program, but it actually produces correct results according to your business logic. You can only apply that if you have pure functions and if you have a type system in your language. So as a bonus, there's the assembly language monad. So some nerd created that, and there are a few commands there that actually work in the same monad and just look like imperative language, just like the assembly language, because they're written in do notation. Okay, I guess that's all I got. And that's my buffet for today. Thank you. Any questions, please? Any at all?
Thank you very much for your talk. This is a special Oscar for you, as usual.
Thank you.
Yeah. I believe he will know what is monad and functional programming is.
Yeah, he will learn about monads soon.
Yeah, definitely. Okay, thank you. And we will continue in 2 minutes with the next speech, and you can ask Alex somewhere.
Yeah, if you have any questions about monads, and not only about monads, just catch me during the break. Thanks.